Hi, welcome everybody, and thanks for watching this video, which is about Anaximander, which is a lightweight approach to support software exploration. And this presentation, the pre-recorded video of a presentation that we've made in the context of the YODA working group for CNRS, Génie de la Programmation et des Langages. So the work I'm going to present here is the work done by a team. My name is Sebastian Mosser. I'm with UQAM, and together with Jean Privat and Laure Gonod, we are working in the context of an INRIA équipe associée project on how to work on software evolution and compiler evolution mainly. But when working on this, we realized that there was like common overlapping with what we were doing before in the group with respect to microservices. And that's why we are going to present in this video like the overlap and the tool Anaximander we are developing to support this exploration. So this presentation is based on two previous work that were published last year, one at ICSoC and the second one at SPLC, related to microservices, and another one at that was rejected and that we are still improving about how to explore software compilers. But you might wonder why a presentation about software exploration and reverse engineering in the context of a like dynamic adaptation working group. Well, basically, initially our objective was to adapt microservices and was to adapt compilers. But before doing this, we realized that you can't adapt what you can't understand. And we really needed a way to better understand the systems we were working with. So that's why we had to take a step back and first try to map and understand the systems and then create the adaptation rule and adaptation systems. So the outline of the video is quite simple. First, we'll go like at an overview of what we call software exploration. Then we'll see based on the SPLC and ICSoC paper, how this can be applied to microservices. And I'll conclude this video by describing how it can be applied to compiler infrastructure like the LLVM one. So first, software exploration. Well, basically, size does matters. So if you consider real-life pieces of software, then you can have a legacy one that exists for a long time. It's a lot of different committers that are involved in writing the source code, and the source code can be really large. This is the example of the evolution of the LLVM compiler infrastructures. It's more than 1,500 different committers, and it's more like 10 million lines of code that represent the infrastructure. So when you enter and when you arrive to work in such a context, it can be quite difficult to understand what's happening. But this is just large software, and we know how to deal with large software. So another interesting dimension in terms of scalability and size is like the number of different technologies that one can encounter in a given system. And microservices, they emphasize this idea because each service is independent. Each service can be defined using a different technology, using different communication protocols, and all these kind of things. So in this case, you have the problem of the large source code and the large amount of code at the global system level. Plus, you have a huge technological mess that you have to dig into to properly understand what's happening in your architecture. So what we encountered is that, well, extracting information from such an architecture, it's really complicated because there's not a silver bullet solution that will give you the precise answer you're looking for. Reverse engineering tools do exist, and they're here to answer the question that we're designed to answer, actually. But if your question is slightly different, it's not the right way of extracting such an information. For example, the LLVM source code, it's C++, so you can reverse engineer C++ code into class diagram, for example, or sequence diagram. But this is not really what you need if you want to understand where to put transformation and transformation paths, for example, inside the paths infrastructure. That's not the kind of information you're looking for. So It really depends on what you want to achieve and what you want to understand for such very large systems. So basically, we leverage the exploration metaphor, and we came back to the ancient Greeks. In 600 BC, Anaximander of Miletus drew the first map of the world, which is on the left. Based on our standard in 2021, this map is obviously wrong. Like, there's no way the world is like this, considering our deep knowledge of the system. But from their point of view, 600 BC, it was sufficient and it was good enough in a way to get a good understanding of the question they were asking. And then by other cartographer and people like interested in geography, like scholars, the map was improved and the map was enriched by adding rivers, by adding mountains, by correcting errors and these kind of things. So that's basically the kind of idea we want to achieve, having a way to explore our system, our piece of softwares this way. So how does it work? Well, basically we consider that one does have a map. It can be the empty map at the beginning, or it can be like a rough idea of what's happening, like a set of like the infrastructure of a compiler, a set of microservices already identified. Like this is roughly a description of the system. Then one rely on exploration probes, like the one we've sent on Mars this week, actually. And a probe is just dedicated to one given task and will be applied to the system. It can be applied on the source code, it can be applied on trace analysis, it can be applied on any kind of artifact, actually, because each probe comes with its own context, let's say, and this produces a partial map. And then, based on this partial map, we'll use a composition algorithm to merge the partial map with the existing map to obtain an enriched map. And then we can iteratively enrich the map and gather more knowledge by applying more probes. So how does it work in a nutshell? Well, basically, so this is tooled in a framework named Anaximander because of the first world cartographer. And the idea is to, for example, here rely on a graph composition engine that we're developing in the team, and we are basically doing here match and merge. So each probe on the left with the microscope returns some information about services and the way they communicate together. And then, in this case, using a match and merge algorithm, we're going to produce the real and concrete map of services communication that is on the right. More precisely, what's an exploration probe? Well, it's basically whatever you want. The only what is mandatory is for a probe to return a model that is compatible with what we call the pivot description language, so the map language, which is basically a graph language. And then a probe can be a static analysis, like here, which is just a visit of the abstract syntax tree to extract information about asynchronous messaging protocol, for example. It can be a trace analysis, it can be digging into a configuration file or a deployment file, it can be whatever. The point is that a probe should be self-contained and provide one given analysis that will help and be reused in a different context. Because if you're exploring like static class hierarchy, you can do it in the context of microservices, or you can do it in the context of compiler, or you can do it in the context of information system. They're the very same. It just needs to be the same language. So if you're exploring C++ code, you need to use the C++ probe, and that's the idea. So how can we apply it to microservices? Well, this work was done in the context of the SPLC, so Software Product Line Conference challenge. And initially we wanted to answer to challenge number 4, which was how to interchange services from one system to another one. The challenge designer, they've identified 6 reference case studies, 6 reference systems, and all those systems were e-commerce, and they wanted to check if one can interchange one customer management service with the one from another system, for example. And what we encounter is that those services it's to do such an interchange, it also needs to, it's required to identify the features and do some feature communication and technology compatibility checking while ensuring loose coupling of the services. So that's why we had to explore the systems first. So what we did first was to identify the feature as a services, and this was done by a manual mapping. Like, this is something related to shipping, so this is a shipping feature and this is a shipping service. This was manual. Even if the software product line community had some feature extraction tools, we did it manually. And then we had to refine the each mapping to the endpoint, to the communication that each service was exposing. And this was done using Anaximander. Like, we're using probes to gather the different endpoints and the way they were connecting together to identify the coupling. And then we had to work on the service dependencies. So as I said, finding how one service was statically calling another service, and also identify code development, because if each time someone write code for service A and it also write code for service B at the very same time, maybe it means that those two services are not such independent. And of course, in this context, the challenge was really to handle the diversity of the different languages, of the different technologies, and all those kind of things. So the approach is available on a GitHub repository. We've published the subpart of Anaximander that is dedicated to microservices, and the subpart of the graph composition engine that goes with this approach. And we followed this idea of taking a probe, for example, related to NoSQL database like MongoDB, taking another probe to get how the Spring framework was used, and we combine all those probes together to build a map that was able to support the how to answer to the challenge. For example, why do we need to compose those probes together, and why do we need such different sources of information? This is an example, so from the SPLC challenge. This system came with an analysis made by a tool called WaveScope that identify, considering Docker containers that are running in an infrastructure, it identifies a TCP connection that goes from one container to another one. So basically it gives you the dynamic relationship that do exist between services. But then you get a lot of different containers that are not part of your system, but that are just like technical containers or things that are living in the server, but that doesn't concern your architecture. So to restrict this to our running system, we use a Kubernetes probe. Kubernetes is a way to deploy services as container in a very coarse-grained view. So we took the description of the service deployment using Kubernetes, and we take the information from WaveScope, and we just compose those two information using an intersection to get what's really deployed in our system and how those systems really communicate with each other. So that's really the idea of having different exploration, different sources of information that we're going to combine to create our map, our version of the system. And for example, the kind of information we do have is like at some point there's a shipping service, there's a queue master that contain orders, and there's this RabbitMQ container in between. But it's just a container, so it doesn't really gives you more information. But if you're working in distributed system, you know that RabbitMQ is used for asynchronous communication. It's like a pub/sub system. So basically, we can use the probe dedicated to explore this kind of system and refine the information, like we were adding rivers or adding mountains in our gross map in the previous slide. Here we are like, okay, I want to explore this communication. So I will just take the RabbitMQ probe and run it on the system. And these RabbitMQ probes give me my useful information that if I want to understand how those two services communicate together, it's done through a topic named Shipping Task Exchange. So in the end, we obtained composed version of the map that were helping us to answer the SPLC challenge. And we've done that for the 6 reference architectures that were given and provided by the designer of the SPLC challenge. And this was using Anaximander, a way to understand what we're working with, and then being able to identify how one service was interchangeable with another service. Something also interesting that here I describe, like, from a very coarse-grained point of view, things related to microservices and communication, but we can also really reuse probes that are totally domain independent. Like, for example, the one that goes into Git commit history. That was really interesting to identify that the green parts on the right represent commits that were done with modification for only one service. So it's like, okay, each service is really independent. But then we also were able to identify clusters of statistically significant divergence of this, where each time you were committing something for the checkout service, you were also committing something to the product catalog, or for shipping and product catalog. So it was more or less giving us information that there was like a tight connection between those two services, at least at the code level. Our ongoing work is to work on the LLVM infrastructure. So it's a compiler infrastructure, and that's what we are working on right now. The idea is, as part of the INRIA associated team we have with Lyon, is to understand how the pass system works and how can we evolve, and how a given pass has an impact on another one. Because when you apply like a -03 optimization level, then you can play up to 90 different passes that are applied several times. Again, the idea here is to go with different sources of information and gather all those information together, because you can do static analysis, like code analysis of the different passes to identify the relationship. Or you can also use dynamic analysis of tracing everything on running benchmarks, for example, to identify how the different passes interact with each other. And what was interesting in this one was that we're able to identify optimization cycles. Like when applying a pass and then another one, we were bringing back the program into a previous state. So applying those two passes one after the other wasn't really pushing the program towards a more organized and more optimized state. To conclude, if you work on large-scale software, it triggers scalability challenges, and those scalability challenges are not just about the size of the source code. It's really about the different dimension and the different sources of information that one can gather together to collect and obtain information about a given piece of software. We are not able to find available reverse engineering tools that were answering our particular question that we had in the microservice way or in the compiler case study. So that's why we wanted to design this very tailored and reusable way of exploring software by composing the result of different probes that one can use. Anaximander is available as an open source toolbox. You can freely download and work with the stuff related to microservices. It's on GitHub. And if you're interested by the compiler one, just drop us an email, and we'll be happy to discuss with you about that. And here are the references of the two papers that were used in this presentation to describe the microservice system. Thank you very much for your attention, and if you have any questions, do not hesitate to shoot us an email, and we'll be happy to answer you. Bye!